Okay, so the first week we talked about, yes, I'm recording it right now, and it is running. So the first week we talked about saturated hydrocarbons. Last week was unsaturated hydrocarbons. Tonight we're going to talk about alcohols, phenols, which is a kind of an alcohol, and ethers. All new types of compounds for you guys' viewing pleasure. Let me hit. I get my dot or no? Oh yeah, okay, cool. So first thing we're talking about is alcohols, which we've already kind of touched on a little bit. So an alcohol is the general formula is ROH, where R is just any carbon chain of any length. And then the OH group is the defining group that makes it an alcohol. This is called a hydroxyl group, the oxygen, a hydrogen. Methanol is the smallest alcohol there is. It's got one carbon chain attached to OH. And this stuff you do not want to drink. Anybody know why you don't want to drink methanol? Don't drink methanol. This actually happened back in the old days, and it was a bad thing. Reason why is it causes blindness. So it's an alcohol, but people would drink it and they would go blind. So this is a very toxic. And it's funny though, ethanol, everybody's favorite compound, is just one more carbon. And this is perfectly non-toxic other than it makes you drunk and dehydrates your body and all that. Isn't that funny? Just adding one more carbon onto that chain just affects the chemistry completely differently. And so this is your R, your two carbon chain with the OH group on the end. And then here is, I think we talked about this last week, isopropyl alcohol is what you, yeah, same with carbon dioxide, carbon monoxide, good point, Anna. Yeah, carbon monoxide is very poisonous. Of course, carbon dioxide is not the greatest either. It's good for trees, but you can die from carbon dioxide as well. But monoxide is very toxic. But anyway, everybody's has in their cabinet probably isopropyl alcohol. And again, this is where you've got a carbon with two other carbons attached directly to it. That makes it the iso. And it's three carbons total, 1, 2, 3. So that's why it's propyl. And this is the common name for that alcohol, rubbing alcohol.
So when a carbon has two carbons off of it, like you were talking, that is considered iso, correct?
That's what causes the iso, yeah.
Got it, thank you.
Okay, so naming rules with alcohol. You're going to find your longest chain that has the hydroxyl group in it. You're going to start numbering nearest the hydroxyl group. You're going to name and locate any other functional groups on the chain. If the OH is on a ring, then that is assumed to be the first carbon. And then you're going to add an ol to the end of the name, OL. So fairly straightforward naming conventions. So here we have 2-methyl-1-propanol. So we've got 1, 2, 3, 4 carbons. Your longest chain is going to be 1, 2, 3. So that's your propanol. The 1 is because you can start numbering at this end. So that's the OH group down here. So at this spot right here. And then you've got this methyl group at the second carbon. So that gives you the 2-methyl. So does that make sense? You got to pick one or the other because you can't get both of these carbons in the same chain. So that's why it's not butanol. It's going to be either 1, 2, 3, or it's going to be 1, 2, 3. You can't, these two aren't contiguous. Everybody see that?
So this is probably a stupid question, but why wouldn't that corner piece be iso?
Because it's really two carbons that's connected to, well, first of all, that could be a common name for this, and we're using this standardized naming convention. So this could be called isobutanol for all I know. It might be possibly called that. So this is a common name, this iso part here. And but when you're naming things according to the IUPAC rules, you're not going to use those kinds of names. Does that make sense?
Yes,
So
thank
this
you.
may be called isobutanol. I don't know. I'd have to go check. All right, over here we've got hexanol, because we've got 1, 2, 3, 4, 5, 6 carbons is our longest chain with the hydroxy group on there. So this is going to be hexanol, but it's 3-hexanol because this is not on the end. And you don't start numbering here and going out because you can't go both ways, right? So you have to go 1, 2, 3. So that's 3-hexanol. And then we've got this methyl group left over, and that's also on the 3rd carbon. So this is 3-methyl 3-hexanol. Any questions there with that? And then here is a ring. So we've got a 6-membered ring with the hydroxy group on it. So this is going to be cyclohexanol. And we said you start numbering with the carbon with the hydroxy group on it. So you got 1, 2, 3 methyl, and then 4 another methyl group. So that's going to be 3, 4 dimethyl cyclohexanol. Oops. And this is not a benzene ring because there's no double bonds inside here. So remember that. Your benzene is your alternating double bonds inside of that ring. So this is not that case. This is a cyclohexane with an alcohol on it. Any questions there? Try to name this puppy. I'll give you a few minutes. Just type the name in the chat when you get it. I'm gonna mute my Alexa before she starts talking sometime during class. Okay, we got one in. Anybody else got some guesses? Or not guesses, answers. All right, got a few more. Okay, got an agreement. All right, looks like we're building a consensus here. Yep, we have 1,2-dimethyl cyclopentanol. So you've got a 5-member ring here with an hydroxy group on it. So that gives you the cyclopentanol. We start numbering on the hydroxy carbon on the ring. So this is 1-methyl, 2-methyl. So that gives us 1,2-dimethyl cyclopentanol. Good job. You can have multiple hydroxyl groups on a chain. So here we've got 2 carbons, and it's got 2 OH groups, 1 on each carbon. And so this becomes a diol. So just like we had an ene and a diene, you're just going to have an all and a diol. So at least it's consistent. You don't have to memorize weird rules about it. And so because it's 2, it's called an ethane diol. And then you tell it the carbons that it's on. So 1, 2 ethane diol is the name of this puppy here. Here's one with 3 on it. So you've got 1, 2, 3 carbons. So that's a propane. And there's 3 hydroxyl groups. So that's a triol. And then you just give the numbers 1, 2, 3. In this particular case, propane triol. Alcohols can have isomers. So here's 1 pentanol. So we've got 1, 2, 3, 4, 5 carbons. The OH group is on the very first carbon. And this is a positional isomer with 2 pentanol. The OH group is just moved over to this carbon. These 2 have the same molecular formula. It's just where the position of the hydroxyl group is at. And so these are positional isomers. And then we have structural isomers because here we still have 5 carbons. They're just now in a plus configuration. And this carbon here is the one with the OH on it. And so you pick the longest chain. We got 3, the longest chain with your hydroxyl group. So that's got to be these 3 carbons here. So that's propanol. It's 1 propanol because the very first carbon has the hydroxy group on it. And then it's the second carbon that has the methyl groups on it. So it's 2,2-dimethyl 1-propanol. This is a structural isomer with both of these guys. All 3 of these have the exact same molecular formula, but this one has a different structure to it. Any questions there about that or the naming of this or anything of that nature? Clear as mud? Okay, glycols is when you have 2 hydroxyl groups on adjacent carbons. So this here again is 1,2-ethane diol. This is what we just saw back here, 1,2-ethane diol. But these hydroxyl groups on adjacent carbons, so they're also frequently called glycols. And this is ethylene glycol because of the 2 carbons here. This is like a common name again for this. And ethylene glycol you may have heard of. Anybody heard of ethylene glycol and what it's used for? Has to do with winter time. Anybody? Anybody? Has to do with your car in the winter. Does that help at all? Anybody? Yeah, Danielle got it. Antifreeze. Ethylene glycol suppresses the freezing point of the water in your radiator, keeps it from freezing and seizing up your engine. And so ethylene glycol is a common component of antifreeze. And by the way, again, if you took this off, you'd have ethanol, right? But putting that other OH group on, you don't want to drink this. This is nasty stuff. And great for your radiator, not good so much for your tummy. Glycerols, also sometimes called glycerins, have 3 adjacent OH groups like this. And these are often used in lotions and soaps and shaving creams because it gives it that, what's the word I want? Kind of like that smooth, slippery kind of texture to it. And this is a common one, 1,2,3 propane triol. I think that was actually on the previous slide as well. So glycerols or glycerins are often used in lotions and soaps and shaving creams. So try to name this guy. We do it on time. Okay, we got one guess in, another one. Anybody else? All right, looks like we've built a consensus here. Yes, this is 1,4-pentane diol. So you got 2 hydroxy groups, so it's a diol. And then you've got 1, 2, 3, 4, 5 with the hydroxy groups on the first and the fourth carbon. So 1,4 pentane diol. Very good. How about, is this a glycol? Yes or no? Okay, Danielle says no. Abby says no. Yep. No again. Yeah, these are not on adjacent carbons, so this is not a glycol. Would this be 2,8 decane diol? Let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yep. And then it's 2, would be 9, right? This is the 9th carbon here. 1, 2, 3. This would be 3,9 decane diol. See that? Yeah, probably lower numbers. You're right. Sorry. Yeah, you're right. 1, and then this would be on the 8th. No, you're correct. 1,8 or 2,8. Sorry. You're correct. Trying to throw me a curveball, eh? All right. Good. We'll go a little bit here and then we'll take a break. So there are different types of alcohols. This is a primary alcohol, and it's called primary because the carbon that it's attached to is only attached to one other carbon. So this is primary. Here we have a secondary alcohol because this attached carbon has 2 other carbons on it. This is a hydrogen down here. So this is considered a secondary alcohol, and then a tertiary alcohol is where it's attached to a carbon that's attached to 3 other carbons like this, and that makes it tertiary. The chemical reactions often vary based on the type of alcohol involved in the reaction, and we'll see some examples of this when we get to the reactants. reactions part. Any questions there about that? Let's just go. It's 3 minutes to 7, so let's just finish this and then we'll take a break. So you can synthesize alcohols. So we've already talked about alkenes. This is a double bond and a hydrocarbon. You can react that with water and sulfuric acid, a strong acid, and this will pop that double bond and will give you an alcohol. So this carbon here, this carbon's going to pick up a hydrogen, and this carbon picks up the hydroxy group. We'll probably be looking at aldehydes and ketones next week or the week after. I'm not sure, but this is the general formula of an aldehyde. You've got some long chain with a carbon with a double bond on oxygen. And you can react this with water and a catalyst, and this will pop that double bond on the oxygen and put a hydrogen on that oxygen, making this into an alcohol. And this is going to be a secondary alcohol because it's attached to, or a primary alcohol because it's attached to one other carbon. A ketone is a chain attached to a carbon with a double bond to oxygen, and then another chain. This R prime here just means it's not necessarily the same chain as this one. It's just some long chain. And again, you can react this with hydrogen and a catalyst, and then now you will get a secondary alcohol because you've got this carbon here attached to two other carbon chains and then a hydrogen down here. And so again, this double bond pops off and the hydrogen attaches to that oxygen. So this is ways of synthesizing alcohol chemically. All right, we'll pause there. And we will take a, why don't we come back at 7:15 and then we will continue. So we'll take a 15-minute break. And I'm going to pause. Oh boy, let's see here. How do I? Somebody wanted me to ask a question at the break. So if you want to talk now, we can.
That was me. So I missed last lecture by accident. It was not on purpose. And so I had to go through chapter 2 on my own. And there's just some things that I was a little confused on and was wondering if we could talk about.
Sure.
Okay. Sorry, I'm getting to the thing. So a friend of mine actually kind of explained hybridization to me, but she didn't explain, like, she pretty much explained to me, what was it? That like SP3 was, I think, 1 bond and like 2 bond, 3 bond, that type of stuff. But can you like go in depth about it, including the sigma and pi bonds?
Yeah, I'm pulling up the slide here.
I think it's slide 11 is where it starts, where I had a question.
Yeah, so if you remember from your previous chemistry class, your s orbitals, let me get to, where do I show I have a slide here. Carbon has 1s2, 2s2, 2p2, right?
Yeah.
The s orbitals look like circles, like here.
Okay.
But your p orbitals look like, I don't know, balloons, figure 8 balloons,
Okay.
infinite signs, whatever you want to call them. And so what you have happening here is that you're taking these molecular orbitals in the outer shell and they're combining together to form what are called molecular orbitals or hybrid orbitals. And so if we go to, let's go back to here. So what's happening is here's the normal ground state of carbon. You've got 2 electrons down here. This is in the 1 shell, it's full. And so this is an inner shell, so it's not going to take place in the reaction, right?
Yeah.
But this 2 shell does. And normally this 2s is full, so it would normally be happy. But you've got this vacant electron up here. This could take, actually these could take 1, 2, 3, 4 more electrons, right? You could put 1 in here, 1 in here, and 2 in there.
Yeah.
But so it will rearrange and form, it'll kick this electron out of the 2s up into the Z like this. This is an excited state. And then it will take all 4 of these and form these hybrid orbitals because they're lower energy. If you think about this vertical axis as being energy, 1s is lower energy than 2s, 2p is greater than 2s. But these sp3s are lower energy than these 2p's are. So nature's lazy, it loves lower energy. So it takes these 4 orbitals and it makes 4 equivalent lower level energy orbitals. And so it's 25% S because there's 1 of those. And then it's going to be 75% P because there's 3 of those. So they're going to look like a balloon here with some S shape to it. Does that make sense?
Yeah.
I didn't really point that out last week, but that's the situation. And so that means you're now going to have 4 outer shell orbitals. They're these molecular hybrid orbitals. And so this is why carbon will form with 4 bonds, is that it's these 4 sp3 bonds. Does that make sense?
Yeah. Yeah. Can you explain, I think it's the slide it's slide 12, like the pi and the sigma. How do you I was trying to look at it and know, oh, that's 3 pi, but I was confused.
All right, well, let's look at this one real quick. So a pi bond are basically p orbitals that are going to bend into each other and overlap. So if you visualize this, these 2 p orbitals are going to bend into each other, and they're going to kind of look like, where's my pen? Let me draw this. Probably would have been good to draw this. And so these 2 guys are going to bend into each other, and they're going to end up looking like this, sort of. And then this one will kind of look like that, right? So they're kind of touching each other, but it's not a complete overlap like this. And so these are weaker because of that. These are strained. So the overall bond is stronger because you have 2 bonds now, right? But this bond is definitely weaker than this one. And so this pi bond, this is called a pi bond when it's a p orbital overlapping each other. This is a sigma bond where it's connecting end to end. And so that's how you can tell. If you go back to, let me clear my drawings and go back to my mouse. You go back here, see these are all single bonds. They're going to be all sp3. This carbon's sp3, this carbon's sp3. So you're going to have 7 sigma bonds. But here, this blue bond is going to be that p orbital, right here. And so
Okay.
that's a pi bond. But you still have the sp, and let me come back here. This is the, move this out of the way. Get it somewhere out of the way. Right? This is a trigonal shape. You've got these 3 sp2 hybrid orbitals, but you still have that 1 p orbital up here. So these 3 guys are going to be the very stable sigma bonds because they're always going to be end on end with whatever they react with. But then this is the guy that's going to bend down, and that therefore is a pi bond.
Got it.
Does that make sense? And you see that
Yeah.
here. And then in the case of ethine, then, or a triple bond, you've got these 2 bending together and then another set of p orbitals bending together. So those are both
Those
pi
would both
bonds.
be pi's.
Yeah, they're both pi's because they're not an end-to-end connection like that.
Okay.
So that
The
gives
next-
you the counts down here with the triple bond and a double bond.
Okay.
Go ahead.
Sorry. So that makes sense. I think the next thing is on slide 39. It's diene isomers. I know we just talked, like you kind of went over them for cis and trans, but the pictures were kind of confusing me. So I was just gonna see if you could clarify on the pictures and how.
Yeah, so what I was trying to show is kind of like I did in the review today. And I don't remember, is this animated? I don't think it is.
No, I don't think so.
But anyway, I probably should make it animated. What I was trying to show is, again, if you draw a horizontal line through here, right? Let me
Yeah.
go back and do that. Oh, I got a straight line. I wonder if I can, let me try that. Ooh, look at that. Okay. So if you draw a horizontal line through this, then you see this methyl group is on the north side of that double bond. And
Yeah.
then all of this whole glob down here is on the south side of that line. So that makes it trans. So that's the red circles was showing the 2 pieces opposite this double bond. The green is showing it opposite here. So if you draw another horizontal line through here, then again, you see that this ethyl group is on the south side and all of this is on the north side. So that makes it trans as well.
Okay.
And then in this case, you've got a trans cis, because if you draw the line through here, these are trans, the red circles are trans. But if you draw a line through here, you see that this ethyl group and this whole glob are on the same side of that double bond. So that gives you the trans cis.
So how do you know what to look at to figure out what is cis and trans to it? So like, how do you know you need to look at the CH3 on the top and then the big glob on the bottom?
You basically ignore your hydrogens.
Got it.
Or you ignore if they're the same thing. You know, so let's say that you, and I realized this the other day that I probably should have given you an example of this. Oh, I got to go back to draw now. So let's say you had like CC, and then up here was like a CH3, CH2.
Yeah.
And down here was a CH3. Oops, this is a double bond. And then up here was a CH3, CH2, CH3. This would be a 2, sorry.
No, you're good.
And then down here was like a CH3. So you're going to ignore these and you're going to look at these guys because they're the ones that are different. Does that make sense?
Got it. Okay, so that makes sense. Yes. So, that makes sense now. Sorry, I had so many questions.
No, it's fine.
So
Everybody
I was
else is probably listening, going, "Oh,
probably,
I'm getting reviewed."
but so I just was looking through the slides. So an alkyne or an alkene, or that is a hydrocarbon with a double or triple bond, right? Because I was looking at it's slide 9. It's way up there.
An alkyne has triple bonds, and an alkene has double bonds.
Got it.
So it's ane, ene.
Yes. Okay. Yep, those are good.
And then if
Sorry.
you have both, you always go with the ine. So if you have a double bond and a triple bond, it's still an alkyne. I think I gave an example of that.
Okay.
Maybe not.
And when there's multiple double bonds is when we do the diene, triene, tetraene,
Correct.
like that stuff.
Yep.
Okay. I think that is all. I think
Cool.
we understood everything else. Thank you so much.
No problem.
Just kidding. Sorry, there was one more thing. The reactions.
After I close my slide deck,
I'm sorry.
the gate is closed, man. All right. Which slide?
It's just the different reactions. So I think I understand addition reaction, like that one, but it was the other ones. Looks like there's slide 45.
45
is the one that from there down is the ones that I don't. So for this one, is it just that the hydrogen gets like split into 2 and put over there?
Yep, exactly. That pi bond's gonna pop.
Okay.
And then this is gonna split apart, and you're gonna put one hydrogen on one carbon and one on the other.
Does it matter which carbons they go on?
They're both hydrogen, so it doesn't matter.
Okay. And is it the same for halogenation? Is it the same?
Unless you're a video gamer, then it's halogenation. Anyway, yeah, same thing. You're going to pop that pi bond. This is going to separate, and you're going to add a chlorine to each side of that double bond that popped.
Okay.
So these are all addition reactions.
Okay.
And then here, you're just going to get the hydrogen on one side and the chlorine on the other. And there's probably a chemical preference for this one, but we're not getting into that level of detail.
Got it. Okay.
Not with an ethene, because it's exactly the same, but there probably is, like if you had another carbon out here, there may be a chemical preference for the chlorine being on the second or the third carbon, but we're not talking about that, so you don't have to worry about it.
Got it.
And then hydration, the same kind of a thing. You're just going to add a hydrogen to one side and a hydroxyl to the other side.
And the reaction is H2SO4?
That's the catalyst. You got to have an acid. It basically helps this water break apart and ionize.
Okay.
So that this bond, it'll react with these 2 carbons over here.
Okay. And I think that was all. I'm looking through to make sure before you close. But and benzene, is that is that when it's cyclic but it has a double bond every other bond, or does it matter?
Benzene, you mean?
Yeah, benzene, sorry.
Yeah, benzene is they're alternating double bonds. You can't have them right next to each other because then these carbons would have 5 bonds on them.
Yeah.
So they have to be alternating. And then, like I said in the lecture, the reality is this is like a shorthand notation. The reality is it's partially double bonded all the way around
Yeah.
in the real world. If
Okay.
that's even real in the real world, right?
That was all. I just checked and double checked. That's all. Thank you.
Okay. All right, are folks back? I want to talk about the syllabus real quick, since I move things around. Can you guys give me a thumbs up or a yay or nay? Are you back? I said 7:15, right? Okay, you're all back. All right, so yeah, I kind of left it up to you guys, but I was kind of wanting to delay it, and because of the fact that we're doing reviews. I wasn't doing that the last 2 times I've taught this class, but I think it's helpful to have that review, and I wanted you guys to get that under your belt. So this first exam then will be this weekend. I've revised the syllabus here to reflect all these changes. And so exam 1 will only be over chapters 1 and 2. So even though we're talking about 3 tonight, that will not be on the exam this weekend. So focus on 1 and 2. And again, I will kick it off Friday at noon, and it'll run to midnight on Saturday, just like we talked before. Nothing's different there. And so tonight we're doing 3. Next week we'll do 4. The following week we'll do 5, but then the second exam will only be over 3 and 4. And this is all detailed up here as well. So exam 2 covers chapters 3 and 4. Which is aldehyde and ketones. Okay, so I figured that was coming next. So 3 and 4 is exam 2. Then we'll do chapter 6 and 7, March 1st. And then exam 3 will be over 5 and 6 only. And then we have a break. That's spring break week. We'll come back and do chapter 8. Why'd I push this off a week? I don't think I needed to. I don't know why. I could probably go either way. Exam 4 will be over 7 and 8, even though we'll be covering 9 and 10. Oh, that's why. I wanted to give you the extra. So we'll do 7 on the 1st. We have a break. We have 8 on the 15th. But then on the 22nd, we'll review chapter 8. And then your exam 4 will be 7 and 8. Does that make sense? And then we'll do 9 and 10 and 11, 12. Again, exam 5 will be only over 9, 10, and 11. And then your final test, exam 6, will be 12 through 15. And we'll probably do like maybe a little review before we start the exam there. I haven't decided yet, but we'll maybe do something with that. Any questions there at all? All right, let's go back to the slideshow then. And I got a, oh, it unpaused recording. I didn't realize that. Okay, I recorded some stuff there. I thought I'd paused it. Okay, physical characteristics of alcohols. Alcohols are polar because you've got, remember we said anything other than a carbon or a hydrogen means it's polar. You've got an oxygen in here. This oxygen is very electronegative, and it is going to pull that electron, even though this is a covalent bond, it's going to pull that electron closer to itself from that hydrogen. And so you're going to get a partial negative dipole moment on the oxygen, and you're going to get a positive dipole moment on the hydrogen. So alcohols are polar, and which means they will dissolve in water because water is also polar. As a matter of fact, mixing alcohol with water, well, I'll talk about that in a minute. I think I'll wait. Okay. This means then that you can have what are called dipole-dipole attractions, because you've got this compound here that's got a negative dipole, partial dipole on the oxygen, and a partial positive on the carbon, and the same thing over here. So that means you've got this partially negative oxygen. You know, remember, these molecules don't exist by themselves. You're in a huge solution of these things. And so it's going to be attracted to a positive carbon. And this is called a dipole-dipole attraction. Everybody see that? And this will increase the boiling point because it will make it more stable. You've got another thing holding this stuff together. So it's going to take more heat to get it to boil and break apart and become a gas. And it will also increase solubility with polar solvents as well. Oops, somebody's bouncing in. Okay, you also have what's called hydrogen bonding. This is where I almost got ahead of myself. So again, you've got an alcohol here, and this oxygen is going to have a partial negative charge to it. But then you've got another alcohol here with a hydrogen that's going to have a partial positive charge on it. And therefore, they can form a what's called a hydrogen bond between the two of these. It's a special extra strong type of dipole-dipole bonding. So this isn't a full chemical bond, it's just this attraction between the two. Hydrogens attached to oxygens, nitrogen, and fluorine all are going to have this because of their high electronegativity. You're going to have the hydrogens be partial positives. But then you could have another alcohol molecule here with the hydrogen on it, with the partial positive, and it could be attracted to this oxygen, and so forth and so on. And this just kind of goes on throughout the whole solution. And so this is why alcohols have hydrogen bonding. And this elevates the boiling point because these things are held together more strongly. And this will also elevate their solubility in polar compounds. Now, do I talk about this in the next slide? Oh, I do. Okay. Water has especially strong hydrogen bonding because the two pairs of oxygen electrons match the two hydrogens. So you've got, in water, you've got H2O, and you've got an electron pair here on the oxygen, an electron pair here on the oxygen. And this means that this can then bond with another hydrogen of another water molecule over here, and it can bond with another hydrogen molecule on this side. So these are particularly strong hydrogen bonds, can be formed with water. And you can also see this happening with, like, this is ammonia. And again, nitrogen is going to have a slight negative charge with this pair of unpaired electrons, and this can bond with other hydrogens, other hydrogen molecules. And then the same thing with fluorine. Still haven't got to the thing I wanted to say. So alcohols will have a higher boiling point than alkanes of a similar molecular mass because of this bonding that goes on between these. And alcohols have a higher solubility than alkanes of similar molecular mass because of the bond that forms between the hydrogen and the alcohol. So, I'm sorry, the water and the alcohol. So here we have a water molecule, partial negative on the oxygen, and then here's an alcohol that's going to have a partial positive on this hydrogen. And so the alcohol can form a dipole-dipole attraction between the oxygen on the water and the hydrogen on the alcohol, and so forth and so on throughout the solution. And this might be, I guess not. Okay, so this is actually why if you mix an alcohol into water, believe it or not, you will get less volume. Does that blow your mind? So if I take and add 1 ml of an alcohol to 20 mils of water, it won't be quite 21 milliliters. There will be a fraction lower than that, and that's because of this bonding is pulling these guys closer together. Isn't that kind of wild? Say yes. Okay. Chemical reactions. Got to keep an eye on time here too. Okay, so we can combust alcohols just like we could combust hydrocarbons. So you have your ROH adding oxygen and heat. You're going to get carbon dioxide and water like any combustion reaction. Nothing too exciting there. You can dehydrate an alcohol. So this is called an elimination reaction, because what you're going to do in the presence of heat and a strong acid like H2SO4, we're going to pop off this hydroxyl group, and we're also going to pop off a hydrogen and form a double bond. And this becomes an alkene, and then you get water as a byproduct. So we're reversing the reaction that we saw last week where we hydrated this double bond into an alcohol. You can have the reverse of that as well. Because remember, everything's in an equilibrium anyway. This really isn't a one-way arrow. It's two ways. Any questions there? This can produce different compounds. So here we have 2-butanol. You've got 4 carbons with the hydroxyl group on the second carbon. If you dehydrate this, you can form either 1 butene or 2 butene, because the double bond can form here, or it, because this OH group is popping off, or it can form in here because that OH, so it can go either side of this carbon atom. So you could get the double bond on this side, or you get the double bond on that side. Does that make sense to everybody? And there's actually a rule. I should have done a history thing on this guy. I didn't think about that. I did it on something else. There was a chemist by the name of Zaitsev, assuming he was Russian maybe, that says that the reaction will favor the double bond with the most alkyl groups. And so what that means is here we've got 1 carbon, we got a methane group on this side of the carbon bond, of the double bond. And here we got a methane on this side. But over here, we've got an ethane on this side. And because there's 2 alkyl groups on 2-butene, you will form more 2-butene from this reaction than you will 1-butene, because this only has 1 R group here, alkyl group. There's nothing over here on this side. Does that make sense? It's a little bit more complicated than that, but for purposes of this class, that's how we're going to roll with it. So because you got 2 on this side, this is going to be more stable. Again, it's lower energy. This will be a lower energy. Nature's lazy, so it likes the lower energy stuff. So it will form more 2-butene than it will 1-butene. Any questions there? And then, like I just said, this is an equilibrium. So you have an alkene over here reacted with water. If it goes in this direction and becomes an alcohol, it's hydration of an alkene. But if you dehydrate this alcohol, then it's going to drive, the reaction will go back the other way. And so what will happen if I add more water into here, assuming you have an abundance of this alkene here? What do you think will happen? Anybody? No ideas? If you add the more water here, it's going to drive that reaction towards the hydration side. And it's going to give you, if you add more reactants, then you'll get more products. But if you pull water out, there's less water to react with this alkene, and so you're going to tend to get the reaction flowing back the other way. Does that make sense? So adding more water will hydrate, removing water will dehydrate. Okay, a condensation reaction of alcohol is you can take 2 alcohols and react them together, and you'll form an ether. ROR is the general formula for an ether, which we'll talk about the end of this class, I think, right? And then you get the water. So this H comes off and this OH comes off of this one. This R attaches to that R, to that O, sorry. So you get the ROR, and then you get water left over. So it's condensing like water, dew condensing on a leaf, or a blade of grass, right? You're getting this water condensing out of these 2 alcohols. And the product of that is an ether. Redox reactions. Redox stands for reduction oxidation reactions. Carbon is oxidized when it loses a hydrogen or it gains an oxygen. Carbon is said to be reduced when it gains a hydrogen or loses an oxygen, sort of the opposite of that. So here we have an alcohol. We've got a carbon with 3 hydrogens on it and an OH group. And with a mild oxidizing agent, you can oxidize this carbon and do a double bond with this oxygen, kicking this hydrogen off and forming your hydrogens as free. And this hydrogen comes off so that it can form the double bond. So this hydrogen come off as 2H, and you get a double bond here between the carbon and the oxygen. This is said to be oxidizing the carbon. And you can think of this as oxidize because you're kind of adding an oxygen bond here. That's kind of how I think about it anyway. And then, of course, the reverse of this would be reducing this carbon. You can break off this double bond and form the alcohol, and that would be a reduction reaction. Okay, primary versus secondary alcohols. Remember I mentioned that earlier tonight. So a primary alcohol, you've got the carbon with the hydroxyl group is attached to one R chain. If you oxidize this, then you're going to get an aldehyde. You're going to have an R, a C, double bond O. One of these hydrogens popped off for that double bond, and you're still going to have this hydrogen here. And so this is an aldehyde, which we'll be talking about next week. But the general formula of that is RC double bond OH. But a secondary alcohol, where you've got two carbon chains attached to this carbon that has the hydroxyl group, when you oxidize this, you're going to end up with this hydrogen popping off, this hydrogen popping off, getting a double bond with the carbon. So now you're going to have RC double bond OR, and this is a ketone. So RCOR is a ketone. Tertiary alcohols, if you had another R group down here, that would make this a tertiary alcohol. They will not oxidize with mild oxidizing agents, so you don't get a reaction at all. Any questions there with that? Everybody kind of follow what I'm doing there? Okay, you can also halogenate an alcohol. We can take alcohol and react it with, usually it's a chlorine or a bromine with a phosphorus. So this would be like PCl3 or PBr3. And with the addition of heat, you will drive off this OH group and replace it with an X. And so you'll get this chain with an X here, either being either chlorine or bromine, in place of this OH group here. And this is called halogenation. And then this phosphorus is going to pick up this OH, and it's going to form phosphorite acid. I don't remember exactly what that is. It's not phosphoric, because that'd be another oxygen here. But don't worry about that. That's a byproduct of it. Any questions there at all? What's happening? You guys are really quiet. You can also do polymerization of alcohols. And so here is an example of a repeating two carbons with a hydroxyl group on it. And then again, remember, this is repeating over and over again to n number of times, n being any numeric value. This is called polyvinyl alcohol, and it's often used in water-soluble films and fibers in the industry. And you can take a glycol, a two-carbon glycol, so this is ethylene glycol, and repeating it over and over again, a super long chain. And this is called polyethylene glycol. It's also abbreviated PEG. This is very viscous, and it's added to shampoos as one of the uses for it, to give the shampoo more body to it. And if you look at your shampoo bottle later tonight, you most likely will see polyethylene glycol as one of the ingredients on the back, or it might say PEG. But that's just this long polymer made up of repeating ethylene glycols. Any questions there? Okay. Oops, somebody's coming back in. All right, we're gonna move on to phenols. What time is it? 7:42. Okay, we'll let's go a bit and then we'll take another break. All right, so phenols are an alcohol, but it's an alcohol in a benzene ring. So here you have your benzene ring. Remember, this is shorthand for the alternating double bonds inside of that ring. So a benzene ring with an OH group on it is called a phenol, but it can have other substituents on it as well. So here's a chlorine on this phenol ring, and here's a bromine and a methane, a methyl group on this phenol group. Phenols are nasty, by the way. So naming rules for a phenol is the same as benzene rings, except the phenol is the base name instead of benzene. And you always start numbering with the OH group, and you number to give smallest numbers. So here, this whole thing is the phenol. This is the number 1 carbon. So then you go 2, 3. So this is 3-chlorophenol. In this one, we've got a phenol, but it's got a methyl group here, and it's got a ethyl group over here. So again, we start with the 1, and we go 2 for the methyl, 3, 4 for the ethyl. So it's 4, but then you alphabetize. So it's 4-ethyl 2-methylphenol. And then here again, we have a phenol with 2 bromines. And so we've got 1, 2, 3, 4, 5. So this is 2,5-dibromophenol. Any questions there at all? Phenols are flammable. They cannot be dehydrated. They cannot be oxidized by mild oxidizing agents, but they can with stronger ones. They can be halogenated where the hydroxy group is replaced by a halogen. And phenols act as weak acids. So they're going to donate protons. Phenols are used, even though it's kind of a nasty compound, it is used in measure in antiseptics. It's also used as antioxidants in food. Antioxidants are an additive put into foods so that they get oxidized before the chemicals in your food do. Thus, it makes your food last longer to have antioxidants added to it. Vitamin E contains a phenol group. Plants produce phenols in their systems, and they are used as an antibacteria in the plants. So these phenol compounds will help plants resist infection of bacteria. Very strong phenols burn, though. They're nasty, nasty. And THC, the active ingredient of marijuana, has a phenol group. I just threw that in there. So you've got this phenol group right here in this overall structure. This is THC. Any questions there? Okay, try to name this bad boy. Give you a few minutes. Okay, Aaron threw an answer at us. Anybody else? Looks like we're building a consensus, perhaps. That's a fairly simple one. You're exactly right. You're going to start numbering here. So this is 2-bromo 3-ethyl phenol. Okay, ethers. Like I said earlier, you're going to have a carbon chain, oxygen carbon chain is the general formula of an ether. Ethers can include benzene rings, so this could be one of the R groups. So you could have a long chain over here, an oxygen, and then a benzene ring. That's also an ether. And it can also contain cyclical hydrocarbons. Like here's a pentane. This is also an ether as well. You either get organic chemistry or you don't. There's my joke that I used to have in the first night, but nobody ever got it. But now you can. So you've got your ROR, you either get it or you don't. And notice that it's got R and then R prime. Again, that's saying that this chain doesn't have to be the exact same as that chain. Okay, the way you name ethers, though, is a little weird. So the OR group is called the alkoxy group. And what you're going to do is you're going to select the longest chain that has the OR in it. And then you're going to change the name of that group. Instead of it being ill, it's going to become oxy. And then you're going to place alkoxy, the alkoxy name, with a locator before the base name. So here, let's look at this example. We've got the longest chain is out here, 1, 2, 3, 4 carbons. And so this becomes butane, and then this becomes methoxy. So this is 1-methoxybutane because it's on this first carbon here of this chain. And this is the methoxy group. Everybody see that? Here, we've got 2 carbons on this side, and we've got 3 carbons on this side with a dangler off the side. So we're going to go with the longer chain, and it's going to be a methyl propane because we've got this extra methyl group here, right? And the 2-methyl because this methyl group is on the second carbon. And then now we have this ethoxy group attached on that very first carbon. So it's 1-ethoxy, 2-methylpropane.
This is probably a stupid question, but is OR the same as O?
Is OR the same as O?
Like next to the ethoxy group, it says equals OR, and then in the chain it has O, and then the CH2 and CH3. So is OR?
This is the R. R can be any length of carbon and hydrogens.
Got it.
Right?
Thank you.
R is just shorthand for that. So that's how you could draw this. R, this could be RO, R prime, because you got 1 carbon chain here that's different than this carbon chain there. Does that make sense?
Yes.
Okay. Any other questions there? It's never a stupid question. If you ask me if grass is green, then I might say that's a stupid question.
Well, we should go down to national.
I did have a question. Can you just explain one more time why the ethoxy name is on there? But you said because that chain is attached to which carbon?
Yeah, so you want to find your longest chain. So in this case, there's 4 carbons on this side of the oxygen, and there's 1 over here. So this is our longest chain. So that makes butane. And then this whole thing, because it's 1 carbon and an oxygen, it's going to be called a methoxy group. You see that? So, and it's attached this very first carbon of this butane. So it's 1 methoxy butane.
Right, that one makes sense to me. It's the second one that I
Okay.
didn't understand as
So
well.
this one, you're going to look for the longest chain, right? On this side, I got 2 carbons.
Right,
On this side, I got 4. But the longest chain I can make is 3.
right.
So this is a propane with a methyl group. But this is still bigger than this one. So this becomes the functional group.
Oh, okay, okay.
And this is your chain. So you get 2 methyl propane, that's this guy right here. And then it's 1 ethoxy, because this whole ethoxy group is attached here. I should have
Right,
drawn
thank you.
boxes around this. It probably would have made it a little bit more obvious.
So do you count, so you were talking about the CH2, and that's what the ethoxy group is attached to. Do you count the CH2 in your original chain?
Can you say that again?
So you were talking about like counting the chain, which did you do the 2 CH3 and then sorry. So can you circle what is the chain and then what is the ethoxy group?
Yeah, so let me draw here again. I'll have to fix this slide for another time. So yeah, so you're looking at both sides of this oxygen, right? So we got 1 side over here. This has got 2. And this side over here has got 3 plus 1, right? So you look at both sides, you go, oh, this is the longer chain. And I've got 3 here, so that's going to give me propane. And then I've got this methyl group on the second carbon, so that gives me 2 methyl. And then now, this whole thing is my ethoxy group. So that becomes 1 ethoxy because it's attached to, that's 1, this is 2, oops, and this is 3, right? So it's 2 methyl, but then it's 1 ethoxy because you're treating this whole thing as the functional group. Does that make
Got it. Thank
sense?
you so much.
And then the same thing over here. You're going to get this guy is your main chain, and this is your whole functional group. So that's the methoxy. Good questions. Any other questions there? Get back to a mouse. Okay. So try to name this guy. Everybody ready for Snowmageddon?
School already got canceled for tomorrow.
Yeah, I saw that for in person. All right, looks like we're building a consensus. I think I have to switch back to my mouse to get it to pop up. Yes, we have 2-ethoxy butane. So again, you've got 1, 2, 3, 4. So that's your longer chain. So that's your butane. And then now you've got 1, 2 carbons on this oxygen. So this whole, this whole thing, I'll come back here. I'll come here. Oh, I forget. I got to click it twice. This is your ethoxy group. So 2 ethoxy, it's on the second carbon. You got 1, 2, 3, 4. So this is 2 ethoxy butane. Good. How about this one? A little bit trickier. Trixie Hobbitzes. Okay, Michelle's throwing an answer out there. And you guys are right, ethoxycyclobutane. So you've got the cyclobutane over here, and then that makes this the ethoxy group. You could put a 1 in there too, that's implied. Good. Okay, ethers can also form isomers. So this is diethyl ether is its common name because it's got 2 ethyl groups on either side. We would call this ethoxyethane. This, by the way, is the most prominent ether out there. And this is an isomer of the oxygen being in the second place over here. So the oxygen can move around in the chain. Same molecular formula, just in a different place. And this becomes 1 methoxypropane because now you've got 3 carbons here. And then this becomes your methoxy group. And then you also can have 2 methoxypropane. A common name is isopropyl methyl ether because you've got an isopropyl group on this side and a methyl on this side. But the proper name is 2 methoxypropane because you've got 3 carbons on this side, and your methoxy group is attached to the second carbon of that chain. But these are all isomers of one another. Any questions there? It's history highlights moments. So I said this diethyl ether is the most common. Diethyl ether was used originally as an anesthetic. And it was a dentist in Boston by the name of William T. Morton who demonstrated in 1842 at the Massachusetts Central Hospital, I think it was, MCH. he did a demonstration showing how ether could be used to knock a person out for surgery. Another surgeon, an actual surgeon, did the surgery on the patient. And but he was basically the anesthetist, right? The one that knocked the guy out. To this day, that surgical theater at that hospital is called the Ether Dome because of that. This is where it was first done. He later went on to serve in the Union Army, where he used ether as they were operating on soldiers. He tried dishonestly to patent ether to make money, and people really criticized him about this. And he said, well, I'm not doing it to make money. I'm just doing it to make sure ether is used responsibly. But he didn't discover ether. He just discovered that it had these anesthetic properties. And so he wasn't able to patent that at all. And how he died is he was actually riding in a carriage with his wife, and he screamed, "Stop the carriage." He jumped out and ran into a river, and he died. And what they think happened was he had a stroke. The stroke caused him to feel really hot, and so he dove into the water to cool himself off, but then the stroke killed him. Poor guy. And believe it or not, there used to be ads for using ether to knock your kids out. So yeah, that's a thing. So it used to be in the old days that when they did surgeries, they used ether to knock you out. Actually, all the way up into, I think, the 1950s, they were still using ether. Did you guys know this about ether, that it was used to knock out patients?
My grandmother said that they used it for her when she was in labor.
Yeah, it was very common for people in that were in labor. They would anesthetize you. Yep. Ether is actually, well, I think I have a slide for this, but it actually can become very explosive, so it's not a safe thing to keep around. But yeah, the other chemical that was used was chloroform. You always see chloroform in the mystery movies and stuff where they knock people out. They put on a rag or whatever and knock them out. That was the one. But ether was safer than chloroform, and so that became the predominant one. The chloroform, the problem with it is that you can easily kill somebody with it by overdosing them with the chloroform, and ether's a little bit safer than that. Oh, here's where I talk about it. So physical and chemical properties of ether. The boiling point is similar to alkanes of the same molecular mass. It's going to be, their boiling points will be much lower than alcohols of a similar molecular mass because the alcohols have that hydrogen bonding. So they will boil more quickly than alcohols will of same molecular mass. Ethers will be more soluble in water than similar alkanes. They can form hydrogen bonds with the water, and so this is why. Ether is very flammable. And then here's where the storage thing is at, is it will react with oxygen to form unstable hydroperoxides and peroxides. So a peroxide is ROOR. So you've got an extra oxygen in there. So that's the reaction with the oxygen, is it goes from ROR to ROOR, a peroxide. And it can also form hydroperoxide, which is ROOH. And these guys are very unstable and will explode. And so because of that, ether is usually stored in a metal container inside of a hood, a ventilation hood, and it has to be periodically checked. What these peroxides and hydroperoxides form is like a crystal crust around the top, and that's what's so explosive. And we used ether in the laboratory when I worked in a commercial lab, and we always had to be, we had a protocol to check it. I forget. It was probably quarterly. I don't think it was as often as monthly, but because it doesn't form that fast. But if you just stick it in the back of a cabinet and let it sit there for a few years, that's when it can get very dangerous. And there have been explosions and deaths due to ether doing that. And ethers can also be halogenated. And I have here a YouTube video of ether blowing up. So I'm going to show this to you guys for funsies.
Fire in the hole! Fire in the hole!
That's just ether exploding. There's no dynamite or anything involved there. It's just the ether.
I like that.
Pretty wild, huh?
You were a kid that was loud.
So that's not something you want to mess around with. So there's always protocols for proper storage and ventilation and making sure that it doesn't form those things. All right. Cyclic ethers also exist. These are rings that have an oxygen in the ring instead of a carbon. So here we have a 3-member ring with one of the points being an oxygen instead of a carbon. Here's like a 5, 4 carbons plus an oxygen. You can even get them with double bonds inside of there, and the oxygen is in the place of a carbon. In the case of, and then here's one with just 6. But notice that's not a benzene because there's not another double bond in there. This is just a diene, a cyclodiene, but it's got an oxygen in one of the places in the ring. And again, THC, our friend, the active ingredient of marijuana, has got that. It's got a cyclohexane ring here, but there's an oxygen in place of one of the carbons. So this THC has a phenol in it, but it also has an ether in it. Okay, there are sulfur analogs of alcohols. And instead of being ROH, there are SH, the sulfur taking the place of the oxygen. And so they get named with the S becoming thio. So here we have 2-butanol, and this becomes 2-butane thiol. So it's 2-butanol because this hydroxy group is on that second carbon, and this becomes butane thiol. This is telling you that this is an SH. And believe it or not, thiols are really important in biochemistry in your body. So it's really kind of fascinating. You don't think about sulfur being that, I don't know. You think of it being more like a nasty chemical than something in your body, but believe it or not, it's in there. Any questions there on that? Okay, thiols have a lower boiling point than their alcohol components. Thiols have a very disagreeable odor because of that sulfur. You know, sulfur usually stinks. And they can be easily oxidized into disulfides. So here we have two ethane thiols. So you got two carbons here with a SH group on the end. This can be oxidized to where you get two sulfurs. So you're taking these two chains, you're popping the hydrogens off and then sticking the sulfurs together. Does that make sense? So this is a disulfide because you've got two sulfurs in there. The general formula for this is RSH plus R prime SH, again, just denoting that this doesn't have to be the same as this chain over here. And you oxidize it, you're going to get hydrogen off. These two hydrogens are going to pop off. And then these sulfides will bond together and you get RSS R prime. We need to get a U over here. U, oh, it's USSR, right? Nah, it won't work. Okay. So this is a disulfide. Any questions there at all? Oh, we didn't take our break, did we? I think we're getting close to the end. Why don't we take a 10-minute break? So let's come back at 8:25, and then we'll wrap up with the rest of the chapter and any questions or anything. Recording again. Okay, just as we had thiols, these sulfur derivatives of alcohol, you can have sulfur analogs of ethers. So instead of ROR, it's RSR. And these are named the same as ethers are, except you're going to use sulfide instead of oxy. So here you've got methylthiomethane. So that's the same length chain on either side. So you just pick one, right? So this is methane, and then this becomes your functional group. So this is methylthiomethane. Over here, well, this is methylthiobenzene. So benzene's your longer R chain, your bigger R chain. So this becomes your methylthio group on this side. And then over here, we've got two carbons on this side of the sulfur, but we've got 1, 2, 3, 4, 5 on this side. We've got a double bond, and we've got a methyl group here as well. So this gives us 2-methyl-2-pentene. That's this chain right here, the 2-pentene for that double bond, and the 2 for the methyl group. And then it's 4, because it's on the 4th carbon, ethylthio. Everybody see that? So this becomes your functional group. And so you have 4-ethylthio, 2-methyl-2-pentene. Any questions there? So try to draw the structure of 3-methyl-1-pentane thiol. And just tell me when you're done, because you won't be able to draw it. And then we'll take a look at it. And I'm going to pick out some problems while you guys are doing that. How you guys doing? Okay, guys, about done. So let's take a look. So what we have here is it's a thiol, so that tells us we have an SH group. It's pentane thiol, so we've got 1, 2, 3, 4, 5 carbons. And then we have 3 methyl, so that means we got to have a methyl group on the 3rd carbon in. And you can count either way in this case. And so we have 3 methyl, 1 pentane thiol. Any, everybody see that? Good. How about this one? What's the name of that sucker? Go ahead, just type the name in there when you get it. Anybody else? That's not a name of a chemical. That was a joke. Yeah, it's a thioether, not a thiol, because you've got RSR. So that's your first hint. All right, you guys ready? And some of you got it. You've got 2 R groups. This cyclohexane is the larger one. So that's your cyclohexane, and then this becomes your methylthiol, sorry. So this is methylthiocyclohexane. This is a sulfur analog of an ether, not an alcohol, because it's RSR, not an SH. Any questions there? Did that help?
So for these types of problems, we're gonna have two separate R groups, and you take the bigger R group?
Yep, just like you do with your other naming conventions.
It's always the bigger one, right?
Yeah, you go with the bigger one.
And the bigger one is what's at the end, and then you put the rest at the front? So like the one that we had right there, that's cyclohexane, and then the rest of this was the methyl.
Right. You're picking this as your base chemical, and this becomes a functional group.
Got it. Thank you.
Mm-hmm. There can be isomers. In this case, a thiol can be an isomer with a thioether because you've got carbon, 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 SH. This has the same molecular formula as carbon S, carbon, carbon, because you've got 1, 2, 3 hydrogens here, 4, 5, 6, 7. And here you've got 1, 2, 3, 4, 5, 6, 8. 8 is this other hydrogen, sorry. That threw me for a second. So you got 8 hydrogens. You've got 1, 2, 3, 4, 5, 6, 7, 8 hydrogens here. So that means you've got the same molecular formula, but one is a thiol, a sulfur analog of an alcohol, and the other one is a thioether, RSR. Everybody see that? So these two can be isomers of one another, even though they're completely different compounds. Pretty wild, huh? I think this is the last slide. And I think I put this in here just because we've been looking at, I'm trying to remember why I added this in the slides, but I think it's just to kind of show you guys, you know, we've done all these different ways of shorthand drawing compounds, but this shows you more of a three-dimensional representation of what these things actually look like. So this is trans 2-hexene. We've got 1, 2, 3, 4, 5, 6. So that's the hex. We've got a double bond here on this second carbon. So that's your 2. And it's a trans because if we go back in here and pick my line and we draw a line down through here. Ooh, it's so cool being able to do a line. We've got this methyl group on one side, and we've got the rest of this guy on the other side. So that makes this a trans. But we draw this. Let me go back to drawing. We draw this like C, double bond, C, right? But this really doesn't show you what it looks like in three-dimensional space. So I think I put this in here just as a reminder that these things exist in 3 dimensions. And this is the structure of what this compound looks like. So, you know, this hydrogen is kind of coming out of the page at you. This one's kind of going back into the page behind you, that kind of a thing. So it's just more or less just to kind of show you guys that there is some three-dimensional structure to these things. And again, here's a benzene ring. Now this is all coplanar. This benzene ring is all in one plane. It's kind of like in the plane 45 degrees coming out of the page kind of a thing. And then you've got one chlorine going back, one is in the plane, and then this one's kind of sticking out of the plane as well. So these things do have three-dimensional structure to them, and it's just something to keep in mind. Oh, I had one more. Yeah, because now here's an example of an even more complex compound. This is vitamin E. And you see how it's kind of got this chain going along here, and then it kind of comes out a little bit and then goes back, and you've got this benzene ring, and you've got a methyl group hanging off here. You've got I think this is probably oxygen going back, and you even have one joining this ring to this whole chain over here that itself kind of turns and goes back in. And why this is useful to kind of see is you can see now more like why certain reactions will occur. Once you kind of see these in 3 dimensions, you could see that this guy is a lot more exposed than this guy. So chances are this is going to be much more reactive because there's just more opportunity for other molecules to come in here and do something with this. Whereas this guy's kind of sandwiched in between these chains, and it would be kind of hard for something to get down in there. Does that kind of make sense? So three-dimensionality does impact the chemistry and the reactions of things. And this definitely becomes very evident in biochemistry. We'll see this a lot because in the body, a lot of your compounds are these giant chain molecules like this, and their geometry affects how they react chemically in the body and how they do things. Any questions there on any of that? My organic undergrad course, I didn't like it all. I actually thought about leaving chemistry after my organic year, my year of organic, my sophomore year, because I just did not like it at all. It was mostly just memorizing stuff, kind of like what we're doing in this class in a way. But if I was thinking about switching to computer science, but if I switched to computer science, which was a brand new degree, by the way, back then, this was in like 82. I know I'm old. But it would have added another year to my, 4-year degree because I was already 2 years into chemistry. And so I just decided, no, I'm going to stick with chemistry. But when I got to grad school, I had to take a graduate level organic chemistry class, and I was dreading it. I was dreading it. I loved the class because it wasn't all memorization. It was more of the whys and wherefores do these reactions happen. And it was looking at, spatial orientation is one component to that affects how things react. And I just really enjoyed that much better than just memorizing reactions. And believe me, you guys are getting nothing like you get in a standard organic chemistry class. There were literally hundreds of reactions you had to memorize. You just walked around with these 3x5 cards and you were just constantly quizzing yourselves. You could even hear people in the school bathrooms doing them in the stall because you just did them every time you had a chance. because there was just hundreds and hundreds of them you had to memorize. So anyway, so I realized during the break that I didn't pick out some 7th edition problems, but I just did that. So I'm going to add them to this slide. And so you guys have them. How many people are using 4th versus 7? Can you type 4 or 7 in the chat or just say it?
I'm using 7.
So it looks like a lot of people are using 7.
That's the one that the college recommended.
Yeah, I know. They didn't really do that very well. So the one thing I will want to point out is that it does look at, I should have looked at this a little bit closer and I didn't. It does look like they're giving you the more modern nomenclature for alcohols. Where did I see this at? So
Did you say that you were going to put the numbers down for us?
yeah, I'll do that right after class. Can't get the page to turn. Yeah, like problem 17. This is in chapter 14, right? It's giving you a different nomenclature than how I just taught you. This is like the newer nomenclature. And this is why Dr. Kincannon doesn't want to go to the 7th edition, because they changed some of the stuff a little bit. So if I was on top of my game, I would have noticed this ahead of time and pointed out to you guys, but I didn't. But what they do is they basically move the, instead of calling it pentanol, they give you like 4 pentan-2-ol. And so if you guys get confused with that, go ahead and ask me a question. We're sticking with the older nomenclature that I taught. And I'll maybe try to send you guys an email about this to explain it or something, or we can talk about it next week in class, or both, just to kind of cover us there. I don't want you guys to get confused with that. So you are going to run into some of the newer nomenclature there. So we'll hook you up with that. Okay, any other questions or anything? So test starts noon on Friday, goes till midnight Sunday. You've got 90 minutes to do it. I think there's like 30 questions, so it's 3 minutes a question is the average. Plenty of time. I don't think most people use the full 90 minutes.
For the test, is like the test gonna be like mostly information from like the lecture, or is it also gonna be like from the lab as well?
No, I don't know what she's doing in the lab. I have no idea. So it's only my lecture, and it's only stuff I covered in the lecture. The books go into some other stuff, but if I didn't talk about it, it's not going to be on the test.
Okay.
So yeah, I don't even know what she's doing. I haven't even seen the labs or anything, so I don't know what you guys are doing in there. You could all be studying Hebrew for all I know. Oh, by the way, I'm wearing my new yarmulke my wife made me. Isn't it pretty cool looking?
Looks great.
A little flowery kind of thing. Any other questions for the test? We'll talk about the test next week as part of our review as well. So if anybody has any big questions from the test or anything, we can talk about those. Okay, well, if not, we are done. I'll add the question numbers for 7th edition. And good luck on the test.
Thank you.
If anything
you.
comes up between now and then, give me a holler.
Thank you.
Thank you. Everyone stay safe.
Yeah, everybody with the storm.